the people that are there on site. Hello to y'all and all of the folks that are out on the Zoom as part of the Zoom connection. This is good to get a chance to make this presentation to you all on the on this some Raspberry Pi and ultrasonic sensor stuff. Before I get started, I want to say thank you to Oak Hill Collaborative for hosting today's talk. Also, a special thanks to Anthony Hake for his technical support and all the work that he put in to the run-up to the Zoom meeting. This tech talk is brought to you in conjunction with the Oak Hill Robotics Makerspace and CTES Labs. The primary activities of the Oak Hill Robotics Makerspace involve building and programming low-cost robots. So, you know, we're not talking about the robots that cost in the thousands of dollars. You know, we try to keep the robot parts common off-the-shelf things that you can get at hobby-level shops or off of Amazon at relatively inexpensive prices. So, those activities involve building and programming low-cost robots to be used for environmental monitoring and water quality monitoring at a community and citizen science level in the Mahoning Valley. So this, our activities are really aimed at the average citizen and the community level. People are interested in environmental monitoring and water quality monitoring, and that have some kind of interest in robotics or automation, that have interest in Arduinos or Raspberry Pis, and they might be interested in some way in applying that knowledge to the environmental monitoring or water quality monitoring. That's like our main thing. And we really are just focused on stuff at the Mahoning, in the Mahoning Valley. The ORM hosts talks like today's talk. We do robot build sessions and robot programming sessions. And so let me just say, anyone that's interested in joining the ORM, it is open. Most of our events are at no cost, but some of the more advanced projects that we're involved in and advanced things that we do have a nominal cost associated with them, but for the most part, it's no cost. Those interested in joining the ORM or collaborating with the ORM, you should get in contact with Anthony Hake, and then we can get something set up, to get you started and see who you are, what you are interested in, and where you would like to participate, in what fashion you would like to participate in. So that's kind of just in a nutshell what the Oak Hill Robotics Makerspace is about. CTES Labs, which is the other group that's sponsoring this today. CTES Labs is a nonprofit facility dedicated to applied research and development of epistemological software systems, with particular focus on environmental monitoring, robotics, and embedded knowledge inference devices. CTES is dedicated to applied research and supports citizen and community science efforts in the areas of sustainability and climate change. And this week is Robot Week at CTES Labs. And this talk is a part of that celebration. CTES Labs has an electronics lab and a that we call ROAM, and a H2O lab that's all about water monitoring. And one of the projects that CTES Labs is doing in collaboration with the Oak Hill Collaborative is the Mill Creek Park Lake project, where the goal is to take underwater robots and get video footage of the lakes in the Mill Creek Park, like Lake Newport and Lake Cohasset, the lakes, the main lakes in the Mill Creek Park. We'd like to get a video survey, underwater video survey of those lakes, and post that video on the websites for the community, just to kind of so everyone can see what's in there, what's under the water. You know, there's some fun things that we saw. You know, some pretty large turtles not too long ago. I was shocked to see turtles that size in Lake Newport. I was very, very shocked. But obviously, there are some surprises in those lakes. And so we would like to get some of the our underwater robot projects involved in doing a video survey for these lakes. Also, the video that we post, we want to make that available to the academic and the research institutions in the Mahoning Valley that are doing image recognition or video recognition with machine learning. That would be very good data for folks doing that kind of research. So that's one of the projects that we have at CTIS Labs, where we're collaborating with the Oak Hill Makerspace folks. So for those of you that are interested, we got the Oak Hill Robotics Makerspace that we do at Oak Hill. And then there's a connection with Oak Hill and CTIS Labs on the Mill Creek Park Lake project. But today we're going to take a look at programming the SR04 ultrasonic sensor connected to a Raspberry Pi. We are assuming that if you are interested in today's talk, and if you're at the talk, that you have either an interest in ultrasonic sensors, the Raspberry Pi, or programming in C++. Here is our intended audience matrix. We use the audience matrix to let folks know kind of, you know, how much technical knowledge is required in the talks that we present. This talk is going to involve some C++. There's going to be Raspberry Pi in the talk. There will be some Linux in the talk. There'll be math and some physics stuff in the talk. It's minor, but the matrix lets you know what level of information or what level of knowledge that you would kind of need to have access to in order to really get the most out of the talks. The matrix is color-coded, so things that are green mean that's letting us know that it's at a beginning or introductory or entry-level kind of knowledge. So, you know, you don't have to be an expert at it. You know, it's pretty much anyone can sit and get something from it. If it's yellow, if an area is marked yellow, that's kind of an intermediate. We expect you to have some kind of knowledge about this. And more than just a passing knowledge, but you don't have to be an expert. But there's assumption that there's knowledge, that you have just a medium amount, if that makes sense. And then if something is marked red, that's going to be an advanced topic, an advanced amount of knowledge, and we really assume for areas in red that you really come prepared and you already understand the concepts and principles involved, and we'll be going over advanced topics. So for the talk today, mostly everything is green. So it's a beginning level stuff, and you have a few things that are intermediate, but they're mild. You know, we don't have a whole bunch of advanced type material today, but there is some stuff that's intermediate, and so you want to keep that in mind. It does require some knowledge of the Raspberry Pi, C++, and Linux. There are also a couple of simple electronic wiring diagrams. You know, and so we tried to keep those simple, and make them as self-explanatory as possible, but they are wiring diagrams. So just be aware of that. And the SR04 sensors that we are talking about today, those are relatively inexpensive. They can be purchased from Amazon, you know, from $5 to $20. You know, there are other sources, so you don't have to go to Amazon. I just wanted to give you guys like a general place where you could buy these from. You can get them in packs of 3 to 10, so it's fairly inexpensive. Inexpensive. Also, the talk that we're doing today is really dealing with the Raspberry Pi 3B plus. Okay, that there's Raspberry Pi 4s out. There are ones that come before the 3B plus. There are, in general, the stuff that we are talking about would apply to any Raspberry Pi. But the Pi can be finicky under certain circumstances. So we're not going to guarantee you that this code runs on every single one. You will have to look at the Pi that you have, and chances are it will run. But if it doesn't, there will be minor changes that have to be made. For instance, some of the earlier Pis had only 20 GPIO pins, and the one that we are using today has 40. And then there are Pi Zeros that kind of have a different configuration, and Pi Nanos that have a different configuration. So just keep that in mind. And we are using Raspbian 4.4 Linux. The C++ that we're using is C++ 14. You would have a little trouble running something earlier than C++ 14. Like if you had C++ 11, you might run into issues with the clock library that we're using for the timing. The earlier versions of C++ hadn't standardized on the clock, the nano clock versus the microseconds clock. So you could run into some issues there. And it just depends on which version of Linux you were running, or which version of Unix maybe, because some people even connect these to Unix, like Mac OS 10. But we're focusing on Linux today, and like I said, it's C++ 14. And we realize that many of the folks that are using the Raspberry Pi, they use Python as their primary programming language. Nothing's wrong with that. Python is a good language, and it can most of the code that we're using today can be easily ported to Python. But we use C++ because it integrates with the other libraries that we're using. We use sensor libraries. We use many chemistry libraries and physics libraries. We use math libraries and artificial intelligence libraries. And those libraries, the ones that we use, they're all true and tried, standard. They scale to very serious applications, and they're already written in C++. And so it's just easier for us to use the C++ language. It's just more compatible with the kind of robotics programming and artificial intelligence programming that we're doing in the general case. So that's why we use C++. And so it's not a shot at the folks that are using Python or some other language. It's just we prefer that because it integrates with everything else that we're doing. And so, in talking about this ultrasonic sensor, let's just get into it a little bit here. The ultrasonic sensor is basically used to measure distance. The sensor is called ultrasonic because it transmits sound waves at a frequency beyond human hearing. So what that means is that as you're using a sensor, although it's called sonic, you won't hear the sound waves that the sensor is generating, is because they're outside of the range of human hearing. They tend to be 25 kilohertz to 50 kilohertz. And in human hearing we can hear things from 20 hertz to 20,000 kilohertz. So sound frequencies that are in that range, we can hear. Sound frequencies that are beyond that range, things that are beyond the 20 kilohertz range are ultrasonic. And sounds that are below that are subsonic, that we can't hear. So that's why that's called ultrasonic sensor, and it's because the waves are beyond our hearing. And just for those of you that are not familiar with the basic use of the ultrasonic sensor, there are three, real basic kind of uses for an ultrasonic sensor. One is as a motion detector. One is a rangefinder, and the other is a combined motion detection and range finding in a single application. So you could have a stationary ultrasonic sensor that can monitor objects that come within its range and that remain there for a certain amount of time. If the thing that you are trying to measure is moving extremely fast, then the ultrasonic sensor won't be able to pick it up. But that would have to be really, really fast, as you're going to see. But in general, if something comes within the ultrasonic sensor's range, it can detect it in most cases. There's some exceptions, but in most cases it can detect it. So you can set an ultrasonic sensor up at a location, and let's say if the ultrasonic sensor has a range of 2 feet, then anything that comes within 2 feet of that ultrasonic sensor would cause the sensor would detect it, right? Ultrasonic sensors can also be attached to mobile devices. And in this case, when they're attached to mobile devices, they're kind of used for range finders, and we use it a lot at the Oak Hill Robotics Makerspace and at the CTES Labs. We use them for robots as range finders. So what it does, as the robot is navigating in some environment, it uses an ultrasonic sensor, one or more, to identify objects that are close. That helps with obstacle avoidance, object detection. The robot wants to know whether something is near or something is far. Ultrasonic sensor can be used. In a lot of cases, for practical purposes, and all of our applications are practical applications. We don't do things just for educational purposes. They're used, in the real world in some way. In most cases, our applications involve multiple ultrasonic sensors. A lot of times we have an ultrasonic sensor on the front of a robot and on the back of a robot. We may have one on either side as well, just to give you some sense, so that the robot has some sense of an ability to detect things in front and back and on either side without rotating. But that would just depend on a build. So in either case, we've got if the sensor is in a stationary location, then you have a situation where the sensor can be used for motion detection. And if the sensor is attached to something that is mobile, that sensor is typically used for range finding. But the third option of combined motion detection and range finding is also something that ultrasonic sensors are used for. For example, there were more than a few folks that during the pandemic they used ultrasonic sensors. They wore them. They made mobile ultrasonic sensors that they attached to a device they wore on a belt, like a pager almost, or, you put in a cradle for like a cell phone, and you put it on your belt or in your pocket or something. And they programmed this device so that if people got within, 3 or 4 or 5 feet or whatever the distance they wanted, their sensor would either a light would come on or a buzz would happen or beep. The system would beep and folks would know, hey, you're too close, or you're either too close to them or you're too close to them or they're too close to you. And so in that case, the ultrasonic sensor was being used as both motion detection and range finding at the same time. And so there are really thousands of uses for these things, checking water levels and the closeness that some device is getting to another device. They're just really countless, and it's up to your imagination as to how you use them. But the key point is that they're used to detect the distance from the sensor to some other thing. An example of motion detector application that would be, used for motion as a motion detector. We have a lot of raccoons and groundhogs that come into our property, and when we're planting things, like we're getting ready to plant some tomatoes, now. We don't want the groundhogs and the raccoons messing around with the stuff we've planted, and so we want to have a motion detection set up so that if some kind of animal, rabbit, groundhog, raccoon is messing around for too long back there, we will be alerted. And so it captures movement and captures things that come within a certain distance. And we'll set our ultrasonic sensor up, outdoor ultrasonic sensor up for that. We use it's a battery scenario, so it will work off a lithium battery for some amount of hours, 10, 12 hours, maybe longer, and those batteries are easy to charge. So as long as our sensor is in something that's protected from the environment and the elements, we're good to go. Like I said, we use ultrasonic sensors also for robots. Our robots, as in conjunction with cameras. Cameras are easily used to take a picture of what it's seeing. Cameras are not always that good at determining the distance it is from the thing that it's taking a picture of. Some are, really sophisticated cameras have more advanced sensor capability, but most cameras just take 2D pictures and cannot really tell you the distance from the robot or from your sensor. So we use the ultrasonic sensor in conjunction with cameras with the robot as a method of range fighting. So just keep that in mind. They can be used for all kinds of things. And our talk today is primarily about HCSR04. That's a very common sensor that's found and used in the Arduino community and the Raspberry Pi community. Chances are, if you run across somebody that's using ultrasonic sensor on the Arduino Raspberry Pi, it's a high probability that it's HCSR04. But I do want to throw a word of caution in here. Although they are used on both platforms, both on the Arduino and the Raspberry Pi, and the code for both, the programming code for the Raspberry Pi and Arduino are similar. They are not exactly the same. There are some functions that are on Arduino that are not a part of the Raspberry Pi programming environment. So you have to keep that in mind. And there are some timing issues with the Raspberry Pi that are not available on the Arduino. The Raspberry Pi is running Linux, and so it's capable of doing multiple tasks at the same time. It could be doing a couple things. You may be downloading music or something and using the Raspberry Pi ultrasonic sensor at the same time. There's multiple things going on. You could have a monitor connected to a Raspberry Pi and doing an ultrasonic sensor and connected to the internet at the same time. And so the Raspberry Pi card has to do multitasking, and it has to be capable of doing multitasking. So that means timing is a little different. Arduino is not running an operating system. It is not generally a multitasking kind of card, a microcontroller, whereas the Raspberry Pi is. And so the timing the timing calculations that you may find in the Arduino world for this HCSR04 may not work precisely on the Raspberry Pi. So I just want to point that out. Just as a note of caution, there's a lot of people that get snagged by that, and they don't realize why their Raspberry Pi ultrasonic sensor is not working, or it's working erratically. And sometimes it gives the right answer, sometimes it gives the wrong answer, or sometimes it gives an answer that's close. A lot of times that has to do with timing. Timing is a big part of ultrasonic sensor processing. So if the timing is off, the ultimate measurement that you get from ultrasonic sensor is going to be off. So just kind of keep that in mind. Whereas the Arduino and the Raspberry Pi are similar, they are not exactly the same. And whereas the code is similar, the code is a little different too. Okay, so here's a let's just do a simple overview for how the ultrasonic sensor works. What it is that we're looking at. Ultrasonic sensor has two basic components. There's a transmitter and there's a receiver. The transmitter component is that part of the sensor that sends out a sound wave. It sends that sound wave out, and ideally the sound wave hits some object, and that sound wave is reflected back to the ultrasonic sensor, and it's received by the receiver. So if you notice in the diagram, we call one of those components a transmitter, and one of those things a receiver, and that's because one sends the sound waves, and the other one captures the reflected sound wave. So that's kind of what's going on there. If an object is in the range of the sound wave, that sound wave will bounce back, and the receiver will receive the sound wave. If there is no object in the range of that sound wave that is transmitted, you won't get back anything. Okay, so keep that in mind. That's what happens. Things have to be in the range of the sensor. The sensor does not have infinite range. It has a limited range. From the time that the transmitter transmits the sound wave to the time it takes for the receiver to receive the sound wave is the measurement that the ultrasonic sensor is actually taking. I want to remind folks that don't remember this. Here's where some of that introductory physics, beginning level physics comes in. The sound travels at 340 meters per second, right? And so that calculation is involved in doing the measurement. So these are not advanced calculations. They're pretty basic calculations, and you can see them on our diagrams through this talk. And they're you can find them in a million places on the internet. The Arduino site on ultrasonic sensors has a pretty good description, a reasonable description of how this calculation works. Also, you should note that the ultrasonic sensor has a minimum distance and a maximum distance. If things are too close to the ultrasonic sensor, it won't see them. It won't detect it. It won't detect the thing if it's too close. And if it's beyond the distance of the ultrasonic sensor, it also won't be able to measure it, right? The sensor cannot detect something that's closer than its minimum distance, and it cannot detect something that is beyond its maximum distance. So in this example, the transmitter and receiver, the minimum distance that can be measured by the sensor is 2 centimeters. So something at 1 centimeter away from the sensor would not be detected. And notice that we have a 4 meter maximum distance. So something that is beyond 4 meters also would not be detected. So the distance, the minimum and maximum distance, is a big deal with ultrasonic sensors. Like I said, you have a transmitter and you have a receiver. The other important thing for the ultrasonic sensor is the measurement angle. That angle, that transmitter is going to send out a sound wave in the form of an angle. It doesn't just transmit sound in a straight beam. It sends it out in an angle. Like if you look at the diagram, it's a 15% angle in this example. Other ultrasonic sensors may have a bigger angle, but here's what the deal is. It's going to send that sound wave out in a 15-degree angle, and it's in all dimensions. It's a 3-dimensional wave. So although the picture only shows it kind of like from a top view, so it looks almost like it's just 2-dimensional going towards the blue wall here, or whatever this object is that it's measuring. You have to imagine that instead of just that 2-dimension, you have to imagine it like a cone. So if you've seen those maybe the cones that you pass on the highway, the orange cones, where it starts narrow at one end and at the top, and it gets a bit broader as it goes to the bottom, and it's in 360 degrees. It's all the way around. Kind of imagine a ultrasonic sensor wave in 3 dimensions like that. So it would be able to pick up, in this case, it would be able to pick up anything within that 15-degree angle. So it would be within the 15-degree angle. It has to be 2 centimeters or more, or 4 meters or less. So for this example, that's what we're talking about. So when you're looking at, so as we talking about this ultrasonic sensor, and using it for either motion detection or range finding, keep in mind there's a transmitter, there's a receiver. It has a minimum distance, it has a maximum distance, and it has a measurement angle. The last thing that you have to kind of think about when you're using a ultrasonic sensor to measure things is the surface type, okay? Now these are the best and easiest thing that you're going to measure is some kind of flat surface that's made out of metal or ceramic or glass or wood or plastic or something like that. And most of the time color is just not even a consideration for the ultrasonic sensor. It's dealing with physical, how waves interact with a surface of some kind, and it works easiest with those kind of sensors. You'll have the greatest amount of accuracy and reliability. But that doesn't mean that you cannot measure surfaces that are not solid, like or flat, right? You certainly, if a person is standing in front of a ultrasonic sensor, it will detect that person. Or if a pet walks past an ultrasonic sensor, it can detect that pet. That pet requires your programming has to be a little more ambitious when you know that you're dealing with irregular shaped objects or objects that are not flat, solid surfaces. You're gonna have to be a little more creative in terms of your programming. If the thing that you're trying to measure is liquid, or a gas, good luck. But under certain circumstances and with the right amount of programming, you may be able to get some results there too. But that would be a very, very, very advanced use of ultrasonic sensor, and it would not be an ultrasonic sensor if you're trying to measure something like a particle. It would not be something that you could just buy off of Amazon, right? So I just want to let you know that in terms of surface types, the easiest ones to measure are flat and solid surfaces, metal, plastic, those kind of things. And it gets a little more challenging if you're talking about soft materials or non-flat materials, but it can be done. We do it all the time. Okay, and so you got a sense, have an idea of what's basically going on with the ultrasonic sensor. If we take a look at the SR04 itself, okay, we're going to see that it has 4 pins on it. And if you notice, the first pin, VCC, is the voltage pin. That's going to take 5 volts. The next pin is called trig. That's the pin that actually triggers the transmitter to send a sound wave. In the diagram, the transmitter is on this left side here, and it's marked with T, if you can see there. And the receiver is on the right side, and it's marked with R. The echo pin carries the signal of the receiver, which receives the sound wave that has been reflected off the object being measured. And so the trig pin actually transmits the sound wave, and that receiver is what receives the sound wave. And the ground pin is for electricity ground. So you got those 4 pins, one representing power, one representing ground, the other one representing the actual receiver and the transmitter. The primary challenge of using the Raspberry Pi with this particular sensor is the sensor uses and requires 5 volts. The Raspberry Pi pins receive 3 volts. So those 4 pins VCC, trig, echo, and ground, those each receive, those are dealing with 5-volt values. The pins, the GPIO pins on the Raspberry Pi, they are typically dealing with 3-volt values. This means that the HC SR04 sensor will send 2 volts beyond what the Raspberry Pi can handle. That lets us know that we have to do some additional work in order to be able to connect the Raspberry Pi to the HC-SO4. Now, there is a HC-SR04P out there that is supposedly rated with 3.3 volts. We've used that from time to time, and in our case, it wasn't reliable. It didn't always work. We had problems with it. Maybe it was just a bad batch, but they aren't reliable yet. And maybe at some point in the future, those 3-volt HC SR04s will be reliable. Maybe they are reliable now. You might want to try it at your own, for your own risk. But we just went with the standard one, and we'll just deal with the conversion of the 5 volts to 3 volts. If you browse the web and looking and you search on how do you connect your Raspberry Pi to this sensor, you're going to see dozens and dozens of examples and projects out there where people use breadboards and capacitors and resistors in the project, and they use that to deal with the difference in voltage between their Raspberry Pi and the sensor. A lot of those work. They're very straightforward. Anybody that has a basic Raspberry Pi kit and the Raspberry Pi breadboard or Arduino breadboard, that will work. There's a lot of good ones. If you go to the Arduino webpage on ultrasonic sensors, they have a pretty straightforward example. They have the breadboard configuration there, how the resistors and capacitors are going to work, and so it's not a big deal. The problem with this approach, though, is that it's tied to a breadboard. And wherever the application or project goes, you got to take the breadboard with it, and that's not convenient for mobile applications and embedded applications. It's difficult to jam that breadboard in there, and so we didn't use that. And so one of the values of this talk today is we're just going to give you a quick overview of how you can get rid of the breadboard and just use a regular TTL converter. In our application, we avoid the impractical breadboard approach by using a TTL to convert the voltage. We use something called TTL leveler, and TTL it's an acronym, stands for transistor to transistor logic. In this case, we soldered our own. This is what they look like here. Take a look at that. And they're cheap, $2, $3. You can get a TTL converter. In the solder, no big deal. It took us maybe a minute and a half to do the soldering. It's very simple soldering. But if if you're not the soldering type, you take a look at these. You can get these off Amazon in packs of 5, 10, or whatever, for between $5 and $10. So it's easy to get these, and using these TTL converters, you do not have to use the breadboard, and you don't have to worry about rating the capacitors and resistors and all that thing. So here's the point: before we can actually use the HC-SR04 with the Raspberry Pi, with an application that's portable or embedded, or some other application that can't afford to be tethered to a breadboard, you need to use a 3.3 volt to 5 volt converter. And so let's take a look at that connection. Okay, we can see here, if we take a look at the wiring, we can see that the 5 volts, how it's connected, and the trig and the echo and the ground is connected. The sensor is connected to the high voltage side of the leveler, and the Pi is connected to the low voltage side of the leveler. So when you get one of these levelers, one side will normally be marked high level, and the other side will be marked low level, or sometimes one side will be marked 5 volts, and the other side will be marked 3 volts, or whatever the conversion is. If you look at the leveler that you have, it'll be marked in some fashion. You want to make sure that the the sensor is connected to the high volt side, and the Raspberry Pi is connected to the low volt side, right? Also, the sensor is not connected in any way to the USB ports or the HDMI port on the Pi. So don't get confused with when we're talking about connecting the sensor to the Pi. Don't get confused with the notion that you might be using a USB ports or the HDMI ports. You won't. You'll be using the GPIO pins. And folks, if you don't know what GPIO pins are or how they work, or you are not familiar with the concept of voltage, ground, input pins, or output pins, don't mess with any of this stuff until you have the proper knowledge and skill. You could easily blow out your Pi or your sensor if you don't know what you're doing. This means that with a couple of wires out of place, you could burn out your $40 or $50 investment. You don't want to go down that road. So if you don't really understand this, don't mess around with it until you do. I would suggest that you take some of the introductory Raspberry Pi classes at the Oak Hill Collab. They have some really great classes. And if they don't have anybody right now that's teaching the class, they know people who are doing Raspberry Pi type presentations. So you want to do that. Notice that we connect that VCC pin from the sensor to the 5 volt pin of the Pi. This allows the Pi to power the sensor. So the Pi can send 5 volts. It just does not receive 5 volts. The sensor needs 5 volts to work. It will get those 5 volts from the Pi. The ground pin on the sensor is connected to the ground on the 5 volt side of the Pi. Notice that the Pi has 2 5 volt pins and 1 3.3 volt pins. We found this connection works best when the ground on the ultrasonic sensor is connected to the 5 volt side of the Pi. The trigger pin is connected to the GPIO pin 23. We don't need to send the trigger pin through the TTL converter because the Pi is sending 5 volts to the transmitter. Okay? The Pi is allowed to send out 5 volts, and that's what the sensor wants anyway. And although the Pi can't receive 5 volts, it can send the 5 volts. So the trigger pin is connected directly to GPIO pin 23. Other GPI pins could have been used in this scenario, but these are the ones we had free on our Pi. So keep in mind that some GPIO pins have some special purposes. It's best to use a generic GPIO pin rather than one of the special GPIO pins if you can, right? The echo pin is the one that sends 5 volts. It transmits 5 volts to the Pi. And since the Pi can only receive 3 volts, this is where that TTL leveler comes in. This is also where people would be using the breadboard. They use that breadboard to deal with that conversion from that echo pin back to the back to the Pi. So we're going to connect that echo pin to the leveler and then connect the leveler to pin 24. And what the leveler is going to do is step down those 5 volts to 3 volts, right? And as long as the 5 volt pin is lined up with the 3 pin, notice in the diagram, they line up. The high level pin is right across from the low level pin. You don't want to have those, the high level pin, on pin number 4 and the low level pin on pin number 2. You want to have those directly across from each other. That way you won't run into any problems. Okay. And once that connection is made, the hardware aspect of this is done. It may sound harder than it is, but for those people out there that's trying to get this done, this is probably going to be a lot of help to you. Also, to see where things are, you can run the GPIO utility on the Raspberry Pi. That GPIO utility will show you what the pin the values are. It'll actually also show you the wiring numbers. There's 2 sets of wiring numbers. There's BCM wiring numbers, and there's WPi wiring numbers. Those both refer to the same thing. And you can use this GPIO facility to see that right before you kind of start running your program. This GPIO utility is a stock part of Raspberry Pi. It shows the BCM numbering and the wiring pi numbers for Raspberry. The BCM stands for Broadcom numbering, is a logical numbering for those pins. And the wiring pi numbering is also another logical numbering. So pins there are kind of three numbers associated with the GPIO pins on the Raspberry Pi. One is just a physical 1, 2, 3, 4, 5, count of the pin from the top of the Pi down to the bottom. And the other two sets of numbers are logical numbers that are used for programming. And typically you don't mix those. You either go with the BCM numbering or with the wiring pi numbering. And so in the wiring pi, they came up that is a part of a library that allows the Raspberry Pi to be programmed like an Arduino using similar type commands. So a lot of people use the wiring pi numbers. As long as you stick with one or the other and you know which ones convert to which ones, you're okay. In our example, we use the wiring pi library. So if you're interested in just, what that GPO, people pronounce it a lot of different ways. GPIO and GPO. There's so many different crazy ways to pronounce that, but I just say GPIO so that we're on the same page. If you want to know what that utility does more, open up a terminal in Linux and type man space GPIO. Remember, I did say that it required a little bit of Linux for this talk, and so my assumption is here that you know how to open up a terminal and that you know what the man pages are, because this is what you would be looking at when you type man space GPIO. That brings up the man page for this utility, and you can see how it's used and what it's talking about. Okay, and so now that we kind of have the hardware configuration of this thing all out of the way, let's just kind of look at a couple of the details of the AC SR04 sensor right quick. You've got the working voltage. We talked about that. You want 5 volts in there. And the current is drawing 15 milliamps. Working frequency is an interesting thing. That's dealing with how many measurements this sensor can take in a second. So hertz is per second, right? So on a good day, if everything is right, you can take 40 measurements in a second, right? That's a lot. That's a lot of measurements, and that's something that you would do programmatically. I don't know. I'm pretty sure someone has pre-built applications already set up for that. But from a programming point of view, that's what that working frequency is. In our case, for this AC SR04, the maximum range is 4 meters. The minimum range is 2 centimeters. And that measuring angle that we talk about was 15 degrees. So our diagram kind of just took advantage of these minimums and maximums in this measurement. And I guess the only other really important attribute for this sensor is the trigger input signal. In order to make that transmitter actually transmit a pulse, you have to have something to activate it. So just sending 5 volts to the ultrasonic sensor will not cause it to automatically just do whatever it does. You first have to send 5 volts, and once it has 5 volts, you send a pulse, a 10 microseconds. You send a pulse for 10 microseconds to that trigger, and that activates the trigger and causes it to send an ultrasonic a sound wave. So you're going to be sending a signal over that trigger wire for 10 microseconds. That's what that US stands for 10 microseconds, and that's enough you don't have to send it longer than that. If you send it shorter than that, it won't activate, and so you'll see where this comes in a little bit. It won't activate. So that's an important kind of number to be aware of, and those that are basically the attributes of that SR04 sensor. Okay, and this is how this is basically the flow of how this sensor works, right? So in software, what you would be doing is you'd initialize the wiring pi library. In our case, you initialize the wiring pi library, and you kind of calibrate the sensor or ping the sensor and give it a little while to wake the sensor up. So that the sensor is live. It's set at values that you want it to be set at, and you could use that GPIO utility at this point to see once you could run your calibration function or your initialization function, and then that would let you know what the transmitter value is. Is that pin a 0 or a 1, and is the echo pin a 0 and 1? That's basically what you're looking at, what those initial values are set at. The next step is you would transmit the signal, and then you receive the signal. And once the signal comes back, you got two simple functions that you perform. You calculate the signal time, the time that it took from the time that the transmitter transmitted the signal to the time that the receiver started receiving the signal. You save that time, and then using that time in our sound calculation time, you're able to calculate the distance. And that's the basic flow for the ultrasonic sensor. I'm going to show a little bit of our ultrasonic sensor class. And the reason why we use a class, and you don't need to use one, if you get on the internet, you'll see plenty of examples of people that have written ultrasonic sensor programs. But the problem with those things are they're throwaway type of programs. They can only be used, in one way. We need to use these ultrasonic sensor measurements in lots of different scenarios with lots of different programs, and things are more flexible, and a lot of things are determined at runtime. And so we can't have a hard-coded kind of program. We need it to be able to work in lots of different situations and lots of different scenarios, and we need it to be reusable. And so we set up a C++ class, and we have ultrasonic class here. And if you look, you notice we have some of the attributes that we have is we keep the distance. We have values for the echo pin and the trigger pin, and we track the current echo pin state and the current trigger pin state. We have a value for the signal in microseconds. That has to do with how long we want that pulse to activate. Remember, we talked about 10 microseconds there. And we need a sound distance ratio. And then we have a lot of getter and setter and calculation methods there. We don't have time to really go over all of these functions. We just wanted you to see that we use the object-oriented design, and actually we have a base class called sensor, and we're going to go over that class in another talk because that's a very useful class to have. It's a very powerful class. That class is a class that we use as a base class for all the types of sensors that we have: cameras and magnetic sensors and pH sensors and conductivity sensors and oxygen sensors. We use lots of different kinds of sensors. And so we have a base class that captures the basic notion of a sensor model. And then our ultrasonic sensor class is derived from that. Now, in order to calculate the echo duration, right, we have two loops. And we measure how long it takes. We capture the state of the pin before we go into the loop. If you take a look at this here where it says the current echo pin state, and we do a digital read in that first loop. And then we continue to do that loop as long as the digital read is equal to the current pin state. And then right after it falls out of that, right, we capture the clock time. Okay, and our clock, with that steady clock now, that's a clock that is a part of the C++ 14 standard library, part of the chrono class. So we use steady clock, and you don't want to use the other ones. There's several different other kinds of clocks. We don't have time to get into all of those here. But for the purposes of this ultrasonic sensor measurement, you want to use a steady clock. And you see where it says here, steady clock end time is equal to steady clock now. That's just capturing what time it is at that moment on the computer. And right up above that, you see start time capture steady clock now as well. Okay, we capture that time. That basically captures, the first one captures the time that the transmitter started transmitting, and the second one captures the time that the receiver started receiving the waves, right? And then we're able to get the duration by subtracting that time, the end time, from the start time, right? And we're able to get the entire elapsed time that way. And then that second calculation is done by taking that, we just use the distance, we calculate that distance that was traveled using that calculation echo duration function. So notice here we have a measure function, and if the value is less than the minimum range or greater than the maximum range, you know you had some kind of problem. Outside of that, that's a very simple and straightforward calculation. Notice though in these functions that we have sleep times, right? In the sleep time, you have that between the digital reads or the digital writes. You use that because these functions are not blocking, meaning that when we call a function, it immediately goes to the next statement. But if the actuator or the sensor that you're using needs time to work, you want to have that wait a little while before it goes to the next statement. So that's what we have those steps there for. But you know, we've kind of gone on as far as we can go, and we're going to post this project, the code, the class for this project on the Oak Hill Robotics Makerspace, so you can get the full C++ class. For those of you that are interested, we'll put like some documentation for how to use it and what we use to compile it, and you're more than welcome to it. And I want to thank Oak Hill Collaborative for hosting this, and Anthony for taking the time to get all of this stuff working. And we hope that those of you that are interested would drop Anthony a note. And now, if there are any questions, please feel free to ask. I think we have time for a few questions, and you can ask me anything on this, and I'll tell you the truth. If I know the answer, I'll tell you what the answer is, and if I don't know, I would tell you I don't know. So please, questions.